Okay guys, in this video we are going to be talking about catalysis. Catalysts are species that can be added to a chemical reaction that will create a new mechanism for the reaction to proceed with. And in the process of doing that, the catalyst greatly speeds up the rate of the reaction. So by providing a new mechanism, the catalyst speeds up the reaction rate, and in the process it is recycled and can be used again and again. And so this has a dramatic effect on the efficiency of the chemical reaction. It's very important in industry, and of course it's also very important in biological metabolism. So as I just said, the catalyst increases the rate of the reaction. It's recycled in the process. It lowers costs. There's three main types of catalysis to think about: homogeneous catalysis, heterogeneous catalysis, and then we'll also talk about enzyme catalysis for biochemical reactions. I think this is just a generic example of catalysis. And so we'll go ahead and go through this. So this is very important in industry. So sulfur trioxide is the precursor to the compound sulfuric acid. I believe sulfuric acid has the record for most tons produced per year. It's probably one of the most important chemical reagents on the planet, and you need sulfur trioxide in order to produce it efficiently. And so the reaction for sulfur trioxide is produced from SO2 and oxygen using a nitrogen monoxide catalyst. These are all pollutants, by the way. In any case, so how the mechanism works is that the catalyst combines with the oxygen to give an intermediate, the NO2, and the NO2 then reacts with the SO2 reactant to produce to recycle the nitrogen monoxide catalyst, and that gives you the precursor. So if you double this reaction, and I believe add it to this one, all of the intermediates in the catalyst will cancel out, and it'll give you this stoichiometric reaction. So the reactivity of the nitrogen monoxide really enables this reaction to take place. I believe the direct reaction may not be so efficient. Another example, this one's relevant to environmental chemistry as well, the reaction of ozone with oxygen radicals, which we saw in the previous talk or the previous video as well. That's facilitated by chlorine catalysts. You may recall that chlorine chlorofluorocarbons are dangerous compounds to the ozone layer. Many years ago, there was a rather large hole in the ozone layer. Due to the release of these compounds, they've since been banned. They're commonly used as cooling agents and propellants in aerosol cans. In any case, the chlorine radicals get into the atmosphere. They react with the ozone to produce the chlorine monoxide intermediate, which then goes on to react with the oxygen radical, freeing up the chlorine, which can then go on to attack another ozone molecule. That's bad, of course, because ozone is responsible for helping to shield the planet from ultraviolet rays from the sun. And so it was a real problem, worthy of consideration. Anyway, this illustrates how the chlorine facilitates the reaction and is recycled in the process, making it very efficient. Here's a diagram showing the potential energy in red of an uncatalyzed reaction pathway. And then for when you have a catalyzed reaction pathway, the reason that the catalyst speeds up the reaction is because it provides a new mechanism, an alternative mechanism, with a lower activation energy. And then when you've got the lower activation energy at the same temperature, that means that there's going to be a higher fraction of molecules that can overcome the barrier, which is going to make the reaction rate constant for the uncatalyzed pathway larger, and so the reaction will be faster. Notice, however, that the energy of the reactants and products are unaffected by the presence of the catalyst. So the delta H is the same. Now this has an effect, or I should say what this implies then, because delta H of a reaction, as we will see, is related to the relative amounts of reactants and products that you'll have at equilibrium. Because the delta H is not affected by the presence of the catalyst, there'll be no effect on the distribution of reactants and products at equilibrium. So while the catalyst will speed up how quickly you get to equilibrium, the catalyst will not make more products for you. Put in another way, suppose you have a reaction that has a 10% yield. Well, the catalyst will speed up how quickly you get to that 10% yield, but it's not going to increase the yield of the reaction. Okay, so that's important to keep in mind. Simple question here. Here's two potential energy profiles. One of them represents an uncatalyzed pathway. The other one represents a catalyzed pathway. Which one is catalyzed? The one with the lower activation energy. These are both endothermic reactions in this case. Here we have some exothermic reactions. Which one's catalyzed? Which one's uncatalyzed? The catalyzed one has the lower barrier. All right, so there's three types of catalysis we're going to talk about. The first one is homogeneous catalysis. This is where the catalyst has the same phase as the reacting species. Both the examples that we looked at previously were homogeneous catalysis. Here's another one. This one's in the aqueous phase. Here, this reaction between cerium, this redox reaction, we'll talk about redox later on in the course, this redox reaction between cerium-4 and thallium plus. Okay, it's very slow on its own. However, if you add a manganese catalyst, it provides an alternate pathway for the reaction to proceed through these bimolecular steps where manganese is oxidized in different ways. The slow step in this mechanism is faster than the direct step, and so this is an example of homogeneous catalysis. Everything's aqueous phase here. In heterogeneous catalysis, the catalyst has a different phase than the reactants. Oftentimes the catalyst is a solid and the reactants are either gases or liquids. What happens is the reactants bind to the solid surface of the catalyst. This can be through physical absorption, that is through weak intermolecular bonds, or the reactants can chemisorb to the solid, that is they can actually react and form bonds with the solid. Either way, a reaction occurs at the solid and then the products are released. And so here's an example of a nickel surface that's a catalyst for the combination of hydrogen and ethylene to produce ethane. So the hydrogens become absorbed on the surface, then the ethylene absorbs on the surface, the hydrogen atoms react with the ethylene at the surface, then the product is released. And of course, the binding site on the nickel surface is then recycled and can be used again and again. Catalytic converters, you've heard of these. These are in your cars. They help to prevent pollution. And so what happens is the dirty emissions from the engine exhaust are pumped through the catalytic converter, which consists of a bunch of different metal, different types of metal. And then at the surface of these metals, pollutants like NO2 will react to form nitrogen gas, which is non-toxic. Carbon monoxide, which is toxic, will be converted into carbon dioxide, which is less harmful than carbon monoxide. Unburned fuel, so octane here, will be further combusted into CO2 and water vapor, thus cleaning up the emissions as they come out, although the CO2 does contribute to the greenhouse effect. Finally, enzyme catalysis. These are Mother Nature's catalysts. Biological organisms use very specific and very efficient protein catalysts called enzymes. Enzymes are very large molecules with molar masses greater than 10 to the 6th sometimes. They don't have to be that big, but they can be. And each of these enzymes has a specific purpose. So the enzyme sucrase is tasked to decompose sucrose into glucose and fructose. That's its sole purpose. And it's very efficient at doing so. The basic idea is that the enzyme, the substrate, which is the compound like sucrose, binds to the enzyme. It forms this enzyme substrate complex where the reaction takes place, and then the products are released, and the enzyme is recycled to go do its business again. Different models for that. The so-called lock and key model is where the enzyme is perfectly shaped to the substrate, so perfectly designed. Sucrase is perfectly designed for sucrose. Only sucrose will fit into sucrase. The reaction occurs, and then the products are formed. Another model, which is, I believe, the more dominant model, is the induced fit model, where the enzyme generally fits to the substrates, but once the substrates bind to the enzyme, then a change occurs in the enzyme which locks them into place. So the induced fit model. So there's it's very subtle. The difference in shapes that you see here is meant to highlight the difference between the lock and key model and the induced fit model. In any case, these are two models for enzyme catalysis. I'm going to go ahead and stop this video here, and we'll get on with the next chapter in the next video.